In this last section of Module 10, we're going to be talking about the future of the climate, and that relies very much on climate modeling. We've got to be able to find a way to predict what's going to be happening in the future, and we've looked at this already in some of the previous material. These next few slides show this sort of two-layer model that we have discussed in previous chapters of the climate, where there's the radiation coming from the surface of the Earth, there's the radiation coming down from the sun that is absorbed by the atmosphere and by the surface of the Earth, and then there's emission of radiation from the atmosphere to space. Now, this is very much similar to the assignment that you're doing in this module, where you're going to be basically setting up a kind of a climate model along this step, where you're actually going to have multiple layers of the atmosphere, and you're going to track energy moving between the surface and the atmosphere and eventually out to space in a simplified way. So we're not really including physics in it, but we're illustrating how these scientific models work, that there is a simplified representation of reality, and then there are some calculations that take place that capture the physics that we know describes how things work from experiments and theories that have been tested by experiments. In your particular assignment, the physics is replaced basically by rolling a die to get an outcome. But you can imagine replacing that die roll step with a calculation of what's the amount of light that's absorbed or emitted by something that would go in there. This figure, which we've also seen several versions of over the course of the semester, is a more detailed rendering of that simple model, where we've got energy flows into and out of the surface and into and out of the atmosphere, and ultimately the Earth is striving to reach an energy balance where the total amount of energy coming in, represented by number 1, the incoming solar radiation in that big yellow arrow in the middle, is balanced by the total amount of energy going out, which is 2 plus 3, the outgoing infrared radiation and the reflected solar radiation. And if those aren't balanced, if there's more energy coming in than going out, the Earth is going to heat up. And if there was more energy going out than coming in, the Earth would cool off. So let's take a look at these in a little bit more detail. Here's your two-layer simplified climate model, where each number represents some of those different physical processes that we saw on that previous slide. So that previous slide sort of had a nice artwork going with it. Here it's just looking at it schematically. And each one of these numbered lines in the model, as it says on the slide here, we can calculate how much that energy flow is from physics, from equations where we know, for example, we put an instrument out to measure how much solar energy comes from the sun, and then that's a number that goes in for 1. There's no equation there, that's just a number. That's the number that we've seen frequently over the course of the semester, the 1360 watts per square meter at the top of the Earth's atmosphere. Sunlight reflected from the atmosphere, that would also be a measurement and just a simple number. But things like item number 7, convection and evapotranspiration, that involves measurements and some calculations related to how much energy is taken away by evaporation from the Earth's oceans. Now, a two-dimensional, in your homework assignment, you're basically doing a one-dimensional model. It's drawn out sort of like this grid here is as two-dimensional, but there's no real meaning to the left and right dimension in your homework. Things go off to the left, they just wrap around to the right, and it doesn't mean anything. A real two-dimensional model for the Earth's climate, the two dimensions would be altitude up from the surface into the atmosphere, and latitude, whether you're near the equator or near the pole, as is illustrated here. And a two-dimensional climate model would track energy as it moves between these different grid cells as illustrated schematically here. And that can be radiation transferring energy between cells. It can also be the physical motion of warm air between those cells, or the physical motion of moisture between those cells. So circulation of the atmosphere and the ocean would all play into the calculation of the flow of energy and the balance of energy for the planet. A three-dimensional climate model would then introduce as well longitude around the planet, and then we would have a full rendering of the surface of the Earth, including where the continents are, what the different albedos or reflectivities are at different points on the Earth. And that's where our state-of-the-art, sophisticated climate models come from. That's or how they're designed, rather, is to fully render, fully represent all the complexity of the Earth, uh, all the details of the continents and the oceans and the oceanic flow and the atmospheric flows. And they run on supercomputers, very, very large networks of computers um, to model this system in as much detail as possible. And this slide is just sort of illustrating a um, difference between a very elaborate climate model, which would be represented by the red curves result, and a simpler model, which is represented by the blue dashed line, where the uh, thing that's plotted here is the temperature change modeling the Earth's climate forward, where carbon dioxide is doubled by 1% each year for 70 years. So that means that after 70 years, the carbon dioxide content had doubled, and then keeping it constant. So that's a kind of computational experiment that can be done with a climate model. And what we see from that is that the temperature goes up, but even after you stop doubling it, so to the right of this uh, black arrow on the left that says transient climate response, there's no more increase in CO2 in the atmosphere, but notice that the temperature continues to rise, and it takes hundreds of years for it to do so. But hundreds of years later, the temperature is still rising because the CO2 is still there, and it takes the planet some time to respond to that. So let's take a look at some of the um, results that we get from these different models. In this particular example, we're looking at the temperature of the atmosphere as a function of altitude. So it's temperature on the horizontal axis, altitude on the vertical axis, and the solid black line shows actual measurements, and all of the other different curved lines show outputs from model predictions. So running these sophisticated computer programs, complicated computer programs to predict what the temperature would be. And you can see that depending on the particular computer program or depending on the particular inputs that were put into them when they started running, they give not all exactly the same answer. All these curves are not lying all on top of each other, but they're all behaving the same way and they're all pretty close to the actual measurements that black curve is showing. They're all within 10 degrees, 10 Kelvin of that black curve, and they're capturing the overall characteristics of it. Um, Here's another example showing global temperature change. Now, not the previous one was like temperature at one instant as a function of altitude. This shows global temperature change over 5 years to model the effect of the Mount Pinatubo volcanic eruption, large eruption in 1991. That put some material into the upper atmosphere that actually prevented some sunlight from reaching the surface and increased the cooling of the planet. And the solid black line, again, are actual temperature measurements, and the two dashed lines are two different climate model simulations. And you can see that they don't capture all of the bumps and wiggles of the actual data exactly, but they do capture the overall trend that the temperature would go down, that it goes down by about 0.5 or 0.6 Kelvin. It reaches a minimum in between 1992, and then over a period of about 4 years, it recovers to what the temperature was before. So these things show us what level of confidence we can have in the climate models. Now, this is perhaps one of the more important slides, and we saw this in the previous chapter, that shows that only when we include human-caused forcings to the Earth's atmosphere in the form of greenhouse gases emitted by human activity, only then do we get model curves, the green set of curves, that agree with the observed temperature. If we do not include human activity and only include natural forcings, we get the blue family of curves. If you look at this and say, why is it diverging in 1960? Remember that we've got feedback effects and that the rate of greenhouse gases going into the atmosphere has been increasing for all of the last 250 years. For a certain period of time, we put in more and more and more and more, and the planet is able to react to that extra input. So we put more CO2 in, but the system of the Earth in the form of absorbing CO2 in the oceans has had a sort of negative feedback effect to absorb the consequences of that extra greenhouse gas going into the atmosphere. And as it happens, then we now see that after about 1960, the Earth's system is no longer able to respond to that forcing. And we're seeing a divergence of those two families of models illustrated in the green and the blue. And it's somewhat similar to the phenomena that we were seeing here, that there is a response that happens after the impulse. So the Earth can't respond instantaneously. As far as, for example, the astronomical seasons go, the hottest day of the year should be the summer solstice, which is June 21st, but the climate takes a little bit of time to respond to that extra forcing, and the hottest months are actually in July and August, not in June. Similar phenomenon here. So if we project our climate models forward, we can make various different assumptions about how much greenhouse gases will be put into the atmosphere by people over the course the next 50 or 100 years and see what sorts of outputs we get. And you can see there's going to be differences between the different computer models, but gradual agreement that the temperatures are going to be increasing by a few degrees. And we have names for these different climate projections that are based on the amount of additional or the total amount of CO2 that goes into the atmosphere. And that's what's written in these numbers on this graph are indicating the number of parts per million for CO2. Currently, we're at around 415 or 420 parts per million, probably depending on exactly when you're watching this video. And it's been increasing steadily. So we're close to this 450 parts per million. Of course, at the rate that we're increasing in 2021 or 2022, we'll be over that 450 pretty soon. So these different projections for the abundance of carbon dioxide in the atmosphere result in different temperature changes. And you can see that they can result in some cases extreme temperature changes of over 3 or 4 degrees Celsius or degrees Kelvin in the future. So we get to these different levels based on the amount of additional watts per square meter of forcing, or rather, I should rephrase that. The levels of CO2 result in a particular amount of energy forcing to the planet measured in watts per square meter. So the RCP numbers are 2.6 means 2.6 watts per square meter of additional heating to the planet due to the presence of greenhouse gases. RCP 4.5, an additional 4.5 watts per square meter. And to stay at this low level here, the RCP 2.6, which you see corresponds to about 400 parts per million in CO2, which we're already past, requires active removal of CO2 from the atmosphere in addition to not putting any more in. If we don't do anything to mitigate things, we're looking at RCP 8.5, continuing high emissions for a long period of time. That gets us to over 1,000 parts per million by the end of this century. And remember on the previous slide that 1,000 parts per million results in a temperature change of more than 4 degrees. And there you're talking about really dramatic changes to the Earth's climate over the course of the next couple of centuries. So that is basically an overview of what the sort of agreements and uncertainties and level of fidelity that you can get from these atmospheric climate models, and how the different projections then are basically affecting the knobs that you turn on those climate models before you run them into the future to see what the outcomes will be. And that means that there's a big range of outcomes possible for us, and to keep the predicted temperature increase low requires a dramatic change in the way people do business, because the models and the data clearly show that anthropogenic activity is explaining the current change that we're seeing in the global temperature. And then finally, this figure just shows that the most extreme temperature changes are places where the temperatures are already extreme, which means at the poles. And so in the Arctic, you can see that we're looking at, for the RCP 8.5 scenario, 10 degrees warmer in the Arctic. That melts all the sea ice up there. That has a feedback effect because ice is more reflective. So then you're absorbing more heat from the sun. So there are a lot of these sort of positive feedback effects that can be triggered by these things.